Picture this, you are standing on a tarmac and right in front of you is a machine so impossibly massive that you could literally pack the entire fuselage of a Boeing 737 inside its outer shell, with room to spare. We are talking about a machine that breathes in tons of air every single second, squeezes it with 60 times the pressure of our atmosphere, and burns it at temperatures that would effortlessly melt ordinary steel. This is the GE9X. It is undisputed heavyweight champion of the skies, built specifically for the Boeing 777X. But the story of this engine isn't just about making things bigger. It's about a crazy paradox where the world's most powerful engine actually uses less brute force in its daily life than its predecessor. It's about custom-engineered pixie dust, 3D printing metal, and pushing the literal laws of thermodynamics on the absolute edge. Before we tear into the guts of this absolute monster, if you enjoy deep dives into the bleeding edge of aviation technology, do me a huge favor. Hit that like button and make sure you are subscribed. It takes just a second, but it really helps push these discussions out to more people. So let's talk about the sheer scale of this thing, because numbers on a screen really don't do it justice. The front fan alone measures 134 inches across. That is almost 11.5 feet of just fan blades. Once you wrap the nacelle, that's the outer housing, around it, the total width comes out to 184 inches. Like I said, a standard Boeing 737 fuselage is only about 148 inches wide. You could slide a 737 right through the engine pod of a GE9X. But here is where it hits out first really fascinating paradox. Because it's so huge, everyone naturally assumes it just blasts out more thrust than anything else in the sky. All day, every day. And technically, yes, it holds the Guinness World Record. Back in November 2017, on a test stand in Peebles, Ohio, GE engineers pushed this thing to a staggering 134,300 pounds of force. To put that in perspective, the fighter jets you see breaking the sound barrier usually max out around 30,000 to 40,000 pounds of thrust. The GE9X crushed the previous world record, which was held by its older brother, the G90. But if you look at the actual certification documents for daily commercial flying, the GE9X is only certified to operate at 110,000 pounds of thrust. The older GE90 actually operates at over 115,000. Why? Why build the biggest, most powerful engine in human history, only to throttle it back for everyday use? The answer is efficiency. The Boeing 777X is a highly aerodynamic aircraft with a massive, glider-like wingspan. It doesn't actually need to muscle its way through the air with brute force like older jets. By building a larger fan but running it at a slightly lower thrust rating, GE dramatically increased the bypass ratio. Let's break down what that means. Because bypass ratio is the secret sauce of modern jet engines. The GE9X has a bypass ratio of 10 to 1. That means for every 1 unit of air that goes into the fiery core of the engine to be compressed and ignite, 10 units of air bypass the core entirely. They are just pushed around the outside of that giant 134-inch fan. That bypass air provides the vast majority of the thrust. And because there is so much bypass air, it creates this massive, relatively cool stream of air that wraps around the superheated, supersonic exhaust shooting out of the core. That shield of air actually acts as a muffler. So despite being the largest engine ever built, GE officially stated that per pound of thrust, the GE9X is the quietest engine they have ever produced. Now, moving that much air requires a very special type of a fan. If you look closely at the front of the GE9X, you'll notice it only has 16 fan blades. You would think a bigger engine needs more blades, but aerodynamics is a funny thing. Fewer blades mean less weight and less aerodynamic drag. But to make 16 blades do the work of 22, they have to be incredibly wide and perfectly shaped. These blades are made of 4th generation carbon fiber composites. They are incredibly stiff, but pure carbon fiber has a problem. It can be brittle. If a large bird strikes a purely carbon fiber blade at 500 miles an hour, it could shatter. So GE engineers added steel leading edges to slide through the air and deflect impacts. And they used fiberglass for the trailing edges to give the blade just enough flexibility to absorb a shock without snapping. But getting this massive fan off the ground presented a massive headache before the engine ever even made it to a Boeing aircraft. Whenever a company builds a new engine, they have to fly it on a testbed plane first. General Electric usually uses a heavily modified Boeing 747. But when they wheeled the GE9X out to their 747-100 test plane, they realized the engine was so ridiculously big that it would literally scrapple the runway. They had to upgrade their test bed to a Boeing 747-400, which sits slightly higher. Even then, Boeing had to engineer a completely custom pylon to attach it to the wing, and they had to tilt the entire GE9X upward by 5 degrees compared to the other 3 engines on the plane, just to give it enough ground clearance during takeoff and landing. Imagine looking out the window of a 747 and seeing one engine that is twice the size of the others, tilted slightly toward the sky. That is what it took just to test this thing. Once the air gets past the giant fan, we enter the core, and this is why the GE9X sounds like the pure science fiction. To get the maximum amount of energy out of a drop of jet fuel, you have to squeeze the air as tightly as possible before you ignite it. The GE9X has an overall pressure ratio of 60:1. The air entering the combustion chamber is compressed to 60 times the pressure of the outside atmosphere. It is violently squeezed through an 11-stage high-pressure compressor. By the time fuel is injected, the air is practically a solid wall of energy. But when you squeeze air that tight and burn it that efficiently, you generate an ungodly amount of heat. The inside of the GE9X reaches temperatures of 2400 degrees of Fahrenheit. That is roughly 1315 degrees Celsius. Normally, engineers solve this by bleeding off some of the cool air from the compressor and channeling it through tiny holes in the turbine blades to keep them from melting. But bleeding off air means you lose efficiency. So GE completely changed the materials. They heavily utilized ceramic matrix composites, or CMCs, in the hottest part of the engine. CMCs are made of silicon carbide ceramic fibers embedded in a ceramic resin. They are 1/3 the weight of metal, twice as strong, and most importantly, they can brush off 2400 degree heat without breaking a sweat. Because they can handle the heat natively, the engine needs 20% less cooling air. That air stays in the main flow path, generating more thrust and burning less fuel. And it's not just ceramics. The GE9X represents a massive shift in how engines are physically manufactured. It features over 250 parts that are additively manufactured. That's a fancy way of saying 3D printed. But we aren't talking about desktop plastic printers. We are talking about electron beam melting, where a high-powered beam fuses layers of titanium aluminate powder micron by micron. The low-pressure turbine blades are 3D printed. The fuel nozzles are 3D printed. By printing these parts, engineers can design complex internal cooling channels that are physically impossible to cast or forge using traditional metalworking. And because they are printed as a single piece, there are fewer welds, fewer joints and less weight. But none of this high-tech wizardry matters if the engine breaks down in the real world. And the real world is incredibly harsh. A huge portion of the orders for the Boeing 777X are coming from Middle Eastern airlines like Emirates and Qatar Airways. These planes are going to be spending thousands of hours flying over expansive deserts, sucking in fine sand and dust. If sand gets into a 2400-degree engine core, it melts into glass, clogs the cooling holes and destroys the engine. GE couldn't just wait and see what would happen, so they went to extreme lengths. They literally hired PhD-level geologists to analyze the exact chemical makeup and consistency of the airborne dust found at cruising altitudes over the Middle East. It's incredibly fine, almost like talcum powder. Back at their testing facility in Ohio, they built a bespoke rig that blasted this custom engineering dirt directly into the core of a running GE9X for thousands of simulated flight cycles. They intentionally tried to choke their own masterpiece to death, just to prove that the 3D printed nozzles and the CMC components could survive the harshest environments on the Earth. When you put all of this together, the 134-inch fan, the 10-to-1 bypass ratio, the 60-to-1 pressure ratio, the 3D printed titanium, and the ceramic composites, you get an engine that is a full 10% more fuel efficient than the GE90, while producing 50% fewer NOx emissions than current regulations require. The GE9X isn't just a bigger engine, it is a fundamental shift in how we move massive amount of weight through the air. As the Boeing 777X finally gears up to enter commercial service, it is going to be riding on the back of an engineering marvel that redefines what is possible in modern aviation. If you made it this far, I really hope you enjoyed this deep dive into the mechanics of the GE9X. Let me know down in the comments what part of this engine blows your mind the most. Is it the 3D printing, the size of the fan, or that crazy pixie dust test? And of course, if you haven't already, please drop a like on the video and subscribe to the channel, so you don't miss our next deep dive into the machines that connect our world. Thanks for hanging out, and I'll see you in the next one.